So this is the syllabus. Okay. For practical. So advanced data structures, algorithm analysis. Okay. So first program enti construct an AVL tree for given set of elements which are stored in a file and implement insert delete operations on the constructed tree. Write contents of tree into new file using inode. సో నెక్స్ట్ ఏంటి బి ట్రీ, దాని తర్వాత ఏంటి మిన్ అండ్ మ్యాక్సీ, దాని తర్వాత ఏంటి బిఎఫ్టి అండ్ డిఎఫ్టి. సో బిఎఫ్టి అండ్ డిఎఫ్టిలో మళ్ళీ ఏమున్నాయి అడ్జసెన్సీ మ్యాట్రిక్స్ అండ్ అడ్జసెన్సీ లిస్ట్. అండ్ నెక్స్ట్ ఏంటి బై కనెక్టెడ్ కాంపోనెంట్. నెక్స్ట్ ఏంటి క్విక్ సెర్చ్ అండ్ మెర్జ్ సార్ట్. నెక్స్ట్ ఏంటి సింగిల్ సోర్స్ షార్టెస్ట్ పాత్. నెక్స్ట్ ఏంటి జాబ్ సీక్వెన్సింగ్. నెక్స్ట్ ఏంటి 0/1 నాప్స్ ఆఫ్ ప్రాబ్లం. అండ్ నెక్స్ట్ ఏంటి ఎన్క్వైరీస్. అండ్ లాస్ట్లో ఏంటి బ్యాక్ ట్రాకింగ్. అండ్ ఫైనల్లీ ట్రావెలింగ్ సేల్స్ పర్సన్. So these are the problems we need to discuss. So as of now, we just got an idea about AVL tree. What is an AVL tree and what it contains? Say sir, no. So remaining all are pending. So don't worry, we will complete it. But you need to understand today and we'll continue tomorrow. Okay. Right. So it may be offline or online. I don't know. But the continuation will be there. Right. So coming to the point, what is an AVL tree? What is an AVL tree? So AVL tree is a height balanced binary search tree. What is the height balanced means? All the left tree elements must be smaller, all the right tree element must be larger, and the balance factor should be only 3, -1, 0 or +1. -1, 0 or +1. So if not -1, if not 0 and if not +1, any other factor may occur. So that tree will become imbalanced AVL tree. Imbalanced AVL tree. Then what we need to do? We need to convert that imbalance to balance by using what? Rotation. How many rotations we have? 4 or 5? So 4 only or not? LL rotation, RR rotation, LR rotation, and so what is the meaning of LL rotation? Left rotation. What is the meaning of RR rotation? What is the meaning of left and right? So left and right means left first and so right and left means right first and so finally every node must carry the factor. So what is the balance factor? Must and should be -1, 0 or +1. So that is called as AVL tree. So by using this AVL tree, so we can perform what operation? We can perform search, we can perform insertion, and we can perform deletion. So very important thing. So there is a procedure to search. Element in a AVL tree. Okay. So in an AVL tree, the search operation is performed with order of log n time complexity. Order of log n time complexity. So what is the time complexity for the search operation in AVL tree? Order of log n. Order of log n. The search operation in the AVL tree is similar to search operation in the binary search tree. So same scenario we follow. We use the following step to search in a AVL tree. So please make a note. So step 1. How many operations we can perform? Search, insert and delete. So for the search operation, what is the first one? Read the element from the user. Read the search element from the user. Read the search element from the user. The step one is read the search element from the user. That means user is going to enter. I would like to search particular amount of particular element. Suppose if I want to search 25, I'll enter 25. Compare the search element with the root node in the tree. Compare, step 2 is compare search element with the value of root element, root node in the tree. The first step is we have to take the search element from the user. The second step is what? We have to compare that captured element and captured element with root node of the tree. Root node of the tree. Step 3. Step 3. If both are matched or if both are same. Both are matched or if both are same. That means the search element and root node of the element is same, so that we found the element. So that we can say that we found the element. So step 3 is nothing but if the search element and root node element is same, so that we can say the element found. So that we can found and terminate the function. And terminate the function. And terminate the function. So here we use condition. Here we use condition. The condition is like search element is one variable and the root element is another variable. So if search element equals to root element, so then we can break the function. We can break the function and we'll end the program. If it is not matched, we'll go for else or another condition. If both are not matched, then check whether such element is smaller than the root node value. If both are not matched, check whether such element is smaller or larger. If both are not matched, check whether the search element is smaller or larger than the node 1. If it is smaller, step 5. If it is smaller, continue search process in left subtree. If search element is smaller or if it is smaller, continue search operation in the left subtree. Left subtree. And step 6. If search element is larger, continue search operation or search process in the right subtree. In the right subtree. In the right subtree. You can write your own understandable language. No need to write as it is. Okay. So first step is what? We have to take the element from the user and after that you have to search with the root node. If there are match, if there is a match search element with the root node, then we will end the process for searching. If it is not match, we'll continue search whether the node element and search element smaller or larger. If it is a smaller, we will check within the left tree. If it is larger, we will check within the right tree. Okay. So this gonna be repeat. So this gonna be step 7. So this gonna be repeat until we find the exact element. Until we'll find the exact element, or leaf node, the search element with the leaf node. Exact element or until the search element compared with the leaf node. That means if the element may inserted or may not inserted. So we have to search until the leaf node. Until the leaf node. There are two ways, right? Either you can find the element or you cannot find the element. If the element is existed, we can get the element. If the element is not exist, we will display like element is not found. Okay, so it is like hall ticket result. Okay, so if I enter the hall ticket, so it will search go and go. So if it is available, it will display the data. So if it is not available, it will display. So no records available for the hall ticket number. The same procedure. Same procedure. So if the element is found, will display and terminate the function. If the element is found, step 8. If the element is found, will display and terminate the function. Will display the element and terminate the function. If the element is found, will display the element and terminate the function. If we reach the end of the leaf, sorry, leaf node, if we reach the leaf node, if we reach the leaf node, we will display element is not found and terminate the function. And terminate the function. Terminate the function. Okay, so this is about search operation within the AVL tree. Search operation within the AVL tree. So totally how many steps are involved? Total 9 steps are involved. What is the first step? You have to take the input from the user. So which element you have to search? That element should be taken from the user. That is the first step. And the second step is what? Compare the search element with the root node. And the third step is what? If both are matched, then we will display the element is found and we will terminate the function. What is the next case? So if they are not matched, then we will check whether the search element is smaller than root or larger than the root. If the smaller one, so we will search within the left tree. If it is larger, then we will search within the right tree. And after that, we will continue until element is found. If the element is found, we will display the element is found and we will terminate. Or else we will continue up to the leaf node of the tree. So if it is still element is not found, then we will display the element is not available and terminate the function. And finally, so these are steps involved in the searching the element within the AVL tree. So based on this instruction, so I can also insert the element into the AVL tree. I can also insert the element into the AVL tree. So those are only a simple 4 types. So first one is what? Insert the new element into the tree using binary search tree insertion logic. What is the binary search logic? What is the binary search tree logic? All the elements should be root node element, smaller element should be in left side and larger element should be in right side. So that one we have to follow. And after inserts, every insertion or every deletion, we have to check the balance factor. We have to check the balance factor. So after balance factor, every node must contain 0, 1 or -1. So if it is 0, 1 or -1, we will continue to insert a new element. If it is not 0, if it is not 1, if it is not -1, we will do the suitable rotation. We will do the suitable rotation. After rotation only, we will insert the new element. So when compared to the search, insertion is easy or not? Say, sir, no. How many steps? Only 4 steps. So first what we need to do? We have to insert the element based on the binary search tree logic. What is the binary search tree logic? All the elements of the root node should be small and all the right nodes of the root node should be capital or larger. So that is one we have to follow. After insertion, we have to calculate. After insertion, we have to calculate balance factor. After insertion, we have to calculate balance factor. The balance factor should be 1, 0 and -1. So if it is 1, 0 or -1, we can go for next element to be inserted. Next element to be inserted. If it is not 1 and if not 0 and not -1, we will do the suitable rotation. Either it may be a LL rotation, LR, RR rotation, LR and RL rotation. And after that, we will go for the again, so balance and after that. Next, deletion operation in the AVL tree. Deletion operation in the AVL tree. So deletion is also nothing but searching the element. Deletion also is nothing but searching the element. So until unless we have to find the element, after finding the element, we will delete the element from the tree. After delete the element, we have to find out the balance factor again. After delete the element, we have to find the balance factor. Either insertion or deletion, we have to find the balance factor and we have to form in a balance tree. We have to form a balance tree. Okay. So this is what about AVL tree. You need to write this program. You need to write this program. So simple. So long question you may get in the examination. You have to write search operation, insert operation, as well as deletion operation, and with this code. So write on the code rastara. First, do not talk, write the program. మేడం చూడండి. యా గుడ్ ఆఫ్టర్నూన్. పర్లేదు పర్లేదు. ఈ అబ్బాయి యొక్క హరీష్ ఉంది. ఓకే ఓకే మేడం. రాయలేదా? స్టార్టింగ్ నుంచి రాయలేదు. పైగా ఎక్స్ప్లెయిన్ చేయాలి, చేస్తాం. Here is your notes. నోట్సే లే. పెన్ ఉందా అట్లీస్ట్? పెన్ను కూడా లేదు. ఆ, ఒక ప్రోగ్రామ్ రాస్తే, ఒక లార్జ్ ప్రోగ్రామ్ ఇదే రాసిన తర్వాత నెక్స్ట్ సైలెన్స్. మాట వినకపోతే అన్ని ప్రోగ్రామ్స్ రాయిస్తా, అన్ని నోట్స్ చెక్ చేస్తా. అందరినీ రాయమన్నాను, ఎవరైతే అల్లరి చేస్తున్నానో వాళ్ళనే 12 ప్రోగ్రామ్స్ రాయమంటాం. ఆ 12 ప్రోగ్రామ్స్ నోట్స్ చెక్ చేసిన తర్వాతనే మీరు బయటకు వెళ్తారు. ఓకే, మీరు కామ్గా ఉంటారో మాట్లాడతారో మీ ఇష్టం. మళ్ళీ పాయింట్అవుట్ చేసిన తర్వాత నేను రాయను అంటే కుదరదు. ఓకే, సో ఇప్పుడే వార్నింగ్ ఇస్తున్నాను మీకు, ఎవరు కూడా డిస్టర్బ్ చేయొద్దు. డిస్టర్బ్ చేస్తే 12 ప్రోగ్రామ్స్ సాఫ్ట్ కాపీ పంపిస్తాను, మీరు కాపీ చేసుకోవచ్చు, ఎగ్జిక్యూషన్ చేసుకోవచ్చు. లేదు అంటే మాత్రం అందరితో పాటు రాయిస్తాను. ఓకే, స్ట్రిక్ట్ వార్నింగ్. మళ్ళీ పాయింట్అవుట్ చేసిన తర్వాత నేను రాయను అంటే కుదరదు. స్పెట్స్, బ్లాక్ షర్ట్, వినిపిస్తుందా? అర్థమవుతుందా? రైట్ బాయ్స్, నాయిస్ వినబడకూడదు. చాలా లెంతీ సబ్జెక్ట్, లెంతీ ప్రోగ్రామ్స్. ఓకే, సో మీరు అండర్స్టాండ్ చేసుకోగలిగితేనే మీరు రాయగలుగుతారు, కానీ సో అండర్స్టాండ్ చేసుకోకపోతే రాయలేరు ఎగ్జామ్లో. ఓకే, డైలాగ్ గుర్తుందా? గుర్తులేదా? చెప్పిన డైలాగ్ గుర్తుంది కదా? డైలాగ్ ఏంటి? ఎవరైతే అల్లరి చేస్తారో వాళ్ళనే రాయమంటారు. ఇట్స్ అ పనిష్మెంట్. గర్ల్స్, సో నా రిక్వైర్మెంట్ ఏంటంటే అట్లీస్ట్ గర్ల్స్ నుంచి ఒక 5 మెంబర్స్ని, బాయ్స్ నుంచి ఒక 5 మెంబర్స్ని సెలెక్ట్ చేయాలి. సమన్యాయం. ఓకే, ఈక్వాలిటీ. ఈక్వాలిటీ ఈజ్ ఎవ్రీవేర్. ఓకే, ఎవరు ఆ లక్కీ గర్ల్స్, ఎవరు ఆ లక్కీ బాయ్ చూద్దాం. నా కాన్సన్ట్రేషన్ మొత్తం మీ పైనే ఉంటుంది, ఎవరు డిస్టర్బ్ చేస్తారా అని. కామ్గా ఉండండి. ఓకే, ఒకటే ప్రోగ్రామ్ రాయండి, మిగతా ప్రోగ్రామ్స్ నేను సాఫ్ట్ కాపీ ఇస్తాను, మీరు డైరెక్ట్గా ఎగ్జిక్యూషన్ చేసుకోవచ్చు. బట్ ఇది లెంతీ ప్రోగ్రామ్, ఇంపార్టెంట్ ప్రోగ్రామ్, గ్యారంటీ ప్రోగ్రామ్. కొంచెం రాస్తే గుర్తుంటుందేమో అని ఇంటెన్షన్తో రాయిస్తున్నాను. ఓకే, ఇంతే, అయిపోయింది. జస్ట్ 80 లైన్స్ ఆఫ్ కోడ్. 80. అందరు రాస్తారా? 12 ఇంటూ 8 సో ఆల్మోస్ట్ 1000-2000 లైన్స్ ఆఫ్ కోడ్స్ ఉన్నాయి, అన్ని ఎక్స్పెరిమెంట్స్ కలిపి. ఓకే, దాంట్లో నుంచి మీకు వచ్చేది 1 or 2 ప్రోగ్రామ్స్ మాత్రమే. ఓకేనా? Okay, completed. Okay, you need to remember this logic. Okay, so major logic is available inside the function called as insert function. Okay, is this calling or declaration? Calling only or not? What is the function name? What is the function name? Insert. So we are supplying how many parameters? Two parameters. One is root, another one is element. And the second one is root and element called as 20. How many times we have called? 1, 2, 3, 4, 5, 6. So 6 times we are calling the same method or not? Yes or no? 10, 20, 30, 40, 50 and lastly 25. Right. So where is the insert method? This is the insert method. This is the insert method. So it contains the node and key. What is key here? The key is nothing but element. The key is nothing but element. So now, what is the value we have in the key? The 10 value we have or not? Yes or no? So it will check whether node is available or not. If it is node is available, then it will return new node. If the node is not available, it will return new node. If the node is available, it will check the key with node key. What is key with node key? So this is entered key and this is already available key. This is already available key. If the key less than root node, if the key less than root node and the left node should be inserted. Okay. Or else, if the key greater than root node, the right node should be inserted. Got the clarity? అర్థమవుతుందా? So, arrow operator. What is the meaning of arrow operator? So, whatever the values are available in the structure with pointer, structure and pointer. So, what are the pointer variable? Left and right. Left and right. So, what is the structure name? Node. So, we are defining a node structure with node variable. So node dot left, if it is a normal structure, what we have? So if it is a normal structure, so structure name, structure tag dot variable name. Yes or no? So if it is a normal variable, structure tag dot variable name. If it is a pointer variable, so we'll use the arrow operator. So okay, so these are the pointer variable. So that is the reason why I can access by using so node left, node arrow right. So insert function, if the key is available, if the key is available, that means the node key is nothing but root node and this key is nothing but the inserting element. The key is nothing but inserting element. If the insert element less than a root node, it goes to the left. It goes to the left. If the insert element greater than the insert element greater than to the root node, it will go to the right node. And after that, and after that, every time, every time, so it will update the balance factor. It will update the balance factor by supplying the node. So balance factor, to find out the balance factor, we have a method called as get balance. We have a method called as get balance. In the get balance, we have written something like this. So we are going to return n when the height of left node minus height of right node. Okay, either it may be a -1, either it may be a 1, or either it may be a 2 or -2 or -3, whatever it is. Directly will return the balance factor. If it is not available, then we are going to return the 0. Got the clarity? Okay, so balance factor, how can we find out the balance factor? So we are going to return the n balance factor, node balance factor. So based on the condition called as height of left subtree minus height of right subtree. So here we are going to get the value actually. That may be a -1 or +1 or -2, -3, -4. It's all based on the element we are inserting into the tree. If the no subtree and no left tree and no right tree, then we are going to return the 0. If the get balance, if the get balance is greater than 1, it's greater than 1 and key is nothing but left. So the get balance is greater than 1 or less than -1. It should not be greater than 1. It should not be less than -1. If it is greater than 1, we are going to use right rotate. If it is less than -1, that means -2, -3, -4, we are going to use left to rotate. We should perform the left to rotate. So if it is not greater than 1, if it is greater than 1 and it is greater than left key, greater than 1, it is greater than left key, here less, here greater than. So we should perform LR rotation. Left rotate first, then right rotate next. If it is less than -1 and less than, here greater than and less than, and less than and less than, then we will perform right rotation and left rotation. So here we are going to perform the RL notation. And after that, all this performed. So for left rotate, for right rotate, so we have separate functions here. That for, so if it is y pointer, will supply the x after rotating. If it is x pointer, we will supply the y after rotating. For this operation, so we have written the left rotate and right rotation operation, and we have the maximum value to find out what are the elements are available, whether the element is maximum elements are inserted or not. So next, height. For height of the left element, for height of the right element. For that, we use this function. So node in the form of height. So if it is not height available, so directly it will return the 0. So this is how you need to remember. So how much you remember the code, that much you can write. So not a problem. Okay, but you have to concentrate and what is the structure and what is the pointer variable, how we can access, and node pointer is available, what is the conditions to apply. So everything we need to learn actually. So we will discuss in the coming classes. Not one, don't worry. So next, coming to the next point. So before that, so see this diagram. See this diagram. So start position. Here is the start position. So we are going to insert the node. We are going to insert the node. If the node is null, if the node is null, there are two conditions, yes and no. If it is yes, you should return the new node. If it is not no, if it is no, so it will nothing but node is already available. Node is already available with some element. We will check what is the key, the element to be inserted into the tree. So if it is less than, we'll go for left subtree. If it is greater than, we'll go for right subtree. Okay. So then return the current node in which node we are inserting. Okay. So update the height. That means factor, balance factor. So check the balance factor. So if it is unbalanced, so based on the condition, we will perform the LL, RR, LR, and RL. Okay. So right rotate and child right, right rotate and right child. And after that, we will return the node. So this is how AVL tree works. This is how AVL tree works. It's all based on the balance factor. It's all based on the balance factor. So if it is less than, so we will go for the left. If it is greater than, we will go for the right. In the again, we have to calculate the balance factor. If it is more than plus value, we will go for the left. If it is minus value, we will go for the right. So if it is not in between the plus and minus, so in middle of the sum of the cases, based on the element, we will perform the LR and RL notations also. Right. Coming to the next point. So AVL tree already we got the idea. AVL tree already we got the idea. So next important factor is B tree. Next important factor is B tree. So B tree is also a specialized MV tree. B tree is also a specialized MV tree that can be widely used in disk access. That can be widely used in disk access. What is the meaning of disk? So long ago we used the CDs and we used the DVDs, right? Yes or no? So in that cases, we'll use this B tree actually. In that cases, we'll use the B tree actually. Okay, so B tree is specialized MB tree that can widely used for disk access. So we can use within the hard disk also. So very important, very important. A B tree of order M can have at most M minus keys and M children. So M is the number of elements. So let us take an example. So if we have the M order M, we have the order M, the simple. So let us assume, so B tree is also nothing but a tree which is ordered tree and which is used to perform the disk operation, which are used to perform the disk operation. The second point is, if m ordered elements are available, if m order B tree is available, so m minus 1 key should be there and m children should be there. What is order of m and what is order of m and what is m minus 1 and m minus 1 keys and what is m children? We will discuss here. Okay, so keep it aside. We will discuss what is M1, what is M minus 1, and what is the children and what is the keys. Okay, so B tree is a M weight tree that can widely used in disk management. And if M ordered elements are available, so M minus 1 key should be there and M children should be there. M should be there. Fine. So the B tree capable to store large number of keys in a single node and large key values by keeping the height of the tree with respectable. Okay, so we will discuss. Okay, as of now, we have seen the tree like this. We have seen the tree like this. This is root, this is left node, this is right node, and this is the node and this is the left node and this is the right node to this left node. Okay, so here 50 is the key, 50 is the key and 40 is the key and 45 is also a key. Suppose a B tree is m ordered key, B tree is m ordered elements, m minus 1 key should be there, m minus 1 keys should be there. Suppose order of m. M is nothing but, let us take an example 3. M is nothing but, let us take an example 3. So simple. So little bit confused, but don't be confused. So finally we will get the idea about the. So let us take an example. M is equal to 3. If order of m B tree is available, how many keys should be there? M minus 1. M minus 1 keys and M children's. M children's. M children's. The children's are nothing but subroots. The children's are nothing but subroots. And what is m minus 1 keys? The keys are nothing but elements. 3 minus 1 equals to 2. Only 2 keys should be there. At most 2 keys should be there. For example, the root is nothing but a key which contain 2 split with 2 split. Key 1 and key 2. Okay, key 1 and key 2. So this is called as order of M B tree. This is called as order of M B tree. So at most 2 keys should be there. Okay, for each and every tree, at most 2 keys should be there. 2 keys and here 2 keys. For the left also we have the 1. Okay, so like this B tree is going to be represented. So observe here, every node in a B tree must contain at most m children, at most m children. Every node in a B tree except the root node and the leaf node contains at least m by 2 children. Okay, so every node in the B tree except root node, the leaf node contains at least m by 2 children. So these are the properties. These are the properties of the B tree. The root node must have at least 2 nodes, left node and right node. All the leaf node must be at the same level. All the leaf node must be at the same level. So these are the properties of B tree. Okay, m children, at most m children, and leaf node must contains at least m by 2 children, and root node must have at least 2 nodes, and all the leaf node must be in level. All the leaf node must be in same level. That means here you can take the example. Here you can take the example. So this is the first level, this is the second level, and this is the third level. So all the leaf node must be in same level. All them must be in same level. You should not construct a tree like this. You should not construct the tree like this. It should be construct a tree in the same level. A tree in the same level, that is called as B tree. That is called as B tree. So what are the properties of B tree? First, all the B tree nodes, all the B tree nodes must contain m children. The first point. The second point, every node in the B tree, the leaf node must at least m by 2 children. M children, m by 2 children, leaf node must be m by 2 children, and at least 2 nodes, and at least in the same level. In the same level. So this is B tree. This is B tree. I will show you one simple example. So rather than this, I will show you simple example. Here, observe. If it is n is equal to 3, create binary tree with order of 3. That is called as a B tree. 1 to 10. 1 to 10. So elements I am going to insert the maximum key. What is the order of n? Order of n is equal to 3. 3 minus 1 equals to 2. At least 2 children's or 2 nodes we have. Okay. First one I will insert. There is no changes. One node and second node. One node and second. I would like to insert 1 to 10 here. I would like to insert 1 to 10 here. Okay. First I have inserted. Second I am inserted. So no change is required. So next 1, 9, 2 are completed. Next element is 3. When I want to insert 3 element. When I want to insert 3 element. Okay. So there is no chance to insert the element at the beside to the 2. Why? Because order of n is equal to 3. That means 3 minus 1 equals to 2. So 3 minus 1 equals to only 2. Only 2 children must be have. So there is no chance for 3 here. So that is the reason why. So we split this children into multiple. So that means the middle value will go up. The middle value will go up. What is the middle value? 2. So 2 will be the root node, and each node must contain two nodes. That is 1 and that is 3. That is 1 left, 3 right. And to the second list, we have 2 again, and right side also we have 2 again. And if I want to insert 4, there is a chance to insert 4 to the beside of 3. Okay, so directly you can insert. When I try to insert 5, there is no chance to the 5. Why? Because 5 is greater than 2. Obviously right side. Obviously right side. The right side 4 is already filled. The right side 4 is already filled. Then what we need to do again? We need to move the middle to top position. Okay, next position. Next, 2 and 4. Root node 2 and 4. In the B tree, so at least m minus 1 key should be there. That means 3 minus 1, 2 keys should be there. So I can place 2 and 4 as the root node, 2 and 4 as the root node, and 1 and to the left, and to 5 to the right, 5 to the right. So there is 3. The 3 is not less than 2, not less than 2, and not greater than 4. So what we have to insert? We have to insert in the middle. We have to insert in the middle. So after inserting the 2, 1, 2, 3, 4, 5, I would like to insert 6. The 6 obviously greater than 4. The 6 obviously greater than 4. So right side to the 4, already the space is available for the 6. So directly we have inserted. Next, when I try to insert 7, the 7 obviously greater than to 4. There is no space at the right side. There is no space at the right side. Again, we have to change this node here. So what are the changes? So we have to write 4. We have to write the 4 and 2 and 1, 6. The greater than 3. So 2 is greater than. So 2 is 3 is greater than 2. So right side of the 2 and 6. So to the 6, 5 is the less than, and 7 is the right side. And I insert 8. Obviously, you can directly insert 8. Next, when I try to insert 9, there is no chance to insert 9 here. Again, we'll split the 6, 7, 8, 9, 10. So all the leaf node must be, all the leaf node must be same line. M minus 1 keys. Every node has 2 children. Every node has 2 children. So this is called as bit. This is called as bit tree. Okay. So got the point. Got the point. So 3 is not possible, will split, and 6 is not possible, will split, and 8 is not possible, will split, and sorry, 8 is possible, 9 is possible, will split, and 10 is possible, directly we can insert. Okay, so this is how we'll perform the B tree. This is how we'll perform the B tree. So just take these steps, only 4 steps, important. So B tree E of order of M contains all the properties. A B tree of order of M contains all the properties of M weight tree. M weight tree. First, every node in a B tree, every node in a B tree contains at most m children. Instead of m, you can use n also. M and n is nothing. Every node in a B tree contains at most m children. Next, second point. Every node in a B tree, every node in a B tree except the root node, except the root node leaf node contains, leaf node contains, except the root node, leaf node contains at least m by 2 children. At least m by 2 children. Third, third, root node must have, the root node must have at least two nodes. At least two nodes. All the leaf node must be at the same level. All the leaf node must be at the same level. All the leaf node must be at the same level. Very, very important. So without this, there is no B tree. So all the leaf node must be at the same level. So don't forget the B tree in a sense, the same level leaf node should be there. And M children, update the first step. M children and M1, M minus 1 keys. M children and M minus 1 keys. Update the first one. Update the first one to m children and m minus 1 keys. Okay. What is a B tree? So B tree is a m way order of tree. What is a B tree? M way order of tree. It contains m children and m1, m minus 1 keys. Except the root tree, all the leaf node must at least m by 2 children and root node at least two nodes, and finally all the leaf node must be at the same level. So that type of tree is nothing but B tree. So you can take this diagram. You can take this diagram so that you will get the clarity. Long question important. B tree, what is a B tree and what are the properties of B tree? Can you explain with an example? You can write this within the examination. Simple. So in today's class, I think you have earned 20 to 25 marks. If you struggle for another 10 or 15, you will get passed within the ADA subject. So what is this concept? Key L less than key R. Left key must be lesser than right key. The same binary search trees concept. Right. Okay. So order of nothing but three: leaf node, keys, binary tree node, children nodes. Okay. We are going to insert 10, 20, 5 and 6. Okay. How many elements we can store? How many elements we can store? Maximum 3 elements. We have defined like that. We have defined like that. If root node must be lesser than max. If root node must be lesser than max, then only we can insert the key. Then only we can insert the key. Otherwise, no full, no split logic this table. Okay. So construct traverse means every children to be satisfied here. So I will execute this program. I will execute this program. So so I will give this program to you so you can execute in the laptop. Simple. So GCC space b3.ca.exe. So node is full, no split logic. And what are the elements we have? So B tree traverser is 5, 10 and 20. So only 3 elements we have taken. So that elements are traversed actually. The traverser means visited. The traverser means visited. So next, there is a concept called as minimum heap and maximum heap. What is the concept? Minimum heap and maximum heap. Simple. So GCC space heap operations a.exe. Original array is 9, 5, 6, 2, 3. And what is the minimum heap? 2, 3, 6, 5, 9. And what is the maximum heap? 9, 5, 6, 2, 3. So minimum heap and maximum heap nothing but ascending and descending order. Okay. Ascending and descending order. So when you see the AVL tree, so AVL tree is nothing but left side tree is nothing but smaller and right side elements are large. But in minimum heap, the minimum heap nothing but first root element should be smaller than all the elements. Sir, smaller than all the element. So this is called as minimum heap. This is called as min heap. So what is the root element? 6. What is the root element? 6. The 6 should be least elements. The 6 should be least elements to the remaining elements. Either may be a left or other may be a right. So 6 is the smallest element. 6 is the smallest element. So 6 to 7, 7 to 10 and 7 to 15. So 6, 7, 10, 15, 12 and 17. So this is nothing but so order descending ascending order and maximum heap nothing but so in minimum heap root value is minimum and in the max heap root value is max. Root value is maximum. So 17 is the root. So can compare to the root element, all the elements are smaller. So this is nothing but min heap and max heap. Min heap and max heap. In the min heap, root must be smaller root must be smaller. In the max heap, root must be capital. So, okay, no need to maintain the same order like binary search tree. So this is the left and this is the right. No need to maintain the order. No need to maintain the order. Okay, right. The next one. The next one is DFS, I think. Yeah. DFS and BFS. DFS and BFS. So already we know that these are the sorting algorithm. These are the sorting algorithm. Depth first search and breadth first search. Just a minute. I will show you the example. Okay. So AVL tree is completed and B tree is completed. Next, minimum heap and maximum heap. Okay. Next, DFT and BFT for given graph. When graph is represented in adjacency matrix and adjacency matrix and adjacency list. Simple. What is adjacency matrix? Right, right. Right. Let us take this example. Right. Observe here adjacency matrix. So let us take n equals to 5. Silence. Let us take an example. N equals to 5. Total 5 elements are available. 0, 1, 2, 3, and 4. 0 to 4 elements are available. So totally 5 elements. So in order to represent in the matrix, in order to represent the same in the matrix, okay, we'll use rows and columns. We'll use rows and columns. We'll use rows and columns. How many elements are available? Totally 5 elements are available. So I can represent 5 by 5 matrix. I can represent 5 by 5 matrix. So 5 by 5 matrix means 5 rows, 5 columns. 5 rows and 5 columns. Simple. Let us take an example. 5 rows and 5 columns. So let us take the scenario. This is the matrix. Pen, pen on the. Okay. N equals to 5. Okay. So 5 by 5 matrix I am going to take here. So simple. Okay. So let us take an example. 0, 1, think. नहीं पेन तो रहा है और था 1, 2. Right. So let us take this example. So for this problem, we are going to represent 5 by 5 matrix. Okay. So 5 rows and 5 columns. 5 rows and 5 columns. The first row and first column. First row and first column. Okay. So let us take an example. 1, 2, 3, 4, 5. So here 1, 2, 3, 4, and 5. So in the adjacency matrix, you have to keep all the zeros in the diagonal. You have to keep the zeros in the diagonal. So let us take this 0, 1, 2, 3 best. Zero, 1, 2, 3, 4. 0, 1, 2, 3, 4. Okay. So 0 and 0 it should be 0. 1 and 1 should be 0. Like this, I will like to display. Okay. All the diagonals are zeros. Okay. For 0 and 0, 0. 1 and 1, 0. 2 and 2 is 0. 3 and 3 is 0. 4 and 4 is 0. The remaining all are 0 and 1. 0 and 1. Link is there or not? If the link is available, so I can place 1. 0 and 2. 0 and 2 not available. So I can place 0. And 0 and 3. 0 and 3 is available or not? So I can place 1. And 0 and 4. So 0 and 4 is not available. Then I'll keep 0. Okay. And for 1 and 0. 1 and 0. 1. 1 and 2. 1 and 2 available 1. And 1 and 3 not available 0. 1 and 4 not available 0. So like this, you have to specify the adjacency matrix. Like this, we have to specify the adjacency matrix. 2 and 0. 2 and 0 is not available. 2 and 2. 0 obviously. 2 and 3. So not available. 0. 2 and 0 not available. 2 and 1 is available. 2 and 3 is not available. 2 and 4 is available. Next 3 and 0 available. 3 and 1 not available. 3 and 2 not available. And 3 and 4 available. So next 4 and 0 not available. 4 and 2 available. 4 and 3 available. And 4 and 0. 4 and 0. 4 and 1 is 0. 4 and 2 is 1. 4 and 3 is 1. So this is called as adjacency matrix. This is called as adjacency matrix. In adjacency matrix, first diagonal will be 0. First adjacency matrix, diagonal elements are 0. The same thing we can represent within the list also. The same thing we can represent within the list also. For 0th element. For 0th element. So 1 is there. 1 is there. Obviously. So 1 is available. So obviously 1 is available. From 1 it is available 2. From 1 it is available 2. So 0, 1 and 0, 3. 1 to 2. Sorry. It is 3, 0, 1, 0, 3. 0, 1 and 0, 3. Next 1. Next 1. So 1 contains 2 and next 1 contains 0. 1 contains 0. That's it. Next 2. 2 is contains 1 and 2 is linked with 4 and 3. So this is nothing but adjacent list. This is nothing but adjacency list. And this is nothing but adjacency matrix. Adjacency matrix. So this is a will represent the model. This is a will represent the model called as adjacency matrix and adjacency list. By using this, So we should represent by using this, we should represent BFT and BFT and DFT. BFT and DFT. Depth first tree and breadth first tree. So GCC space graph travels and A dot ex. So this is called as adjacency matrix. All the diagonal elements are 0. All the diagonal elements are 0. Remaining all are 1, 9, 1, 0, 1, 1, 1. So it's all based on the elements. It's all based on the elements to the length. So what are the elements? 0, 1, 3, 2, 4. So this is DFS and this is BFS. Okay. So what is the difference between DFS and BFS? So DFS used to depth. So used to perform the depth analysis and BFS used to perform the line by line. So step by step, near by near. So near by near. So traverse the element. Traverse the element means so it will visit each and every element in the tree. Each and every element in the tree. So so generally, so DFS, so generally DFS used as stack performance. So generally DFS used as stack. So stack means lost in, first out. Lost in, first out. So BSF is nothing but like Q. BFS is nothing but like Q. So Q follows FIFO order. First in, first out. So what is the use of this traverser? So this BFT and DFT is nothing but tree traverser algorithms. Tree traverser algorithms. What is the meaning of traverser? Means whatever the elements are available or vertices or vertex, whatever the vertex are available, all the vertices should be visited. All the vertices should be visited. So DFS will go to the depth first search. Will go to the depth first. So how much you learn have the tree, that much will go inside first. And coming to BFS, so it will not go directly into the depth. So it will touch each and every element which is near, So that is the DFT and BFT. It is similar to DFS and BFS. So this is called as adjacency matrix and this is called as adjacency list for the elements called as 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So this is how you have to write the examination. So DFS and BFS. So so we have discussed something about binary tree, binary search tree, AVL tree, B tree, and minimum heap, maximum heap, and as well as DFT and BFT. DFT and BFT. So in DFT and BFT, so we have discussed that adjacency matrix and adjacency list. Adjacency matrix and adjacency list. So we will deliver this all the codes to you so you can practice out and you can copy the programs and you have to read and you have to so write in the examination. Okay. So remaining subject and remaining things so we need to discuss so in the coming classes. Okay. Right. సో ఐడియా వచ్చిందా మీకు డేటా స్ట్రక్చర్స్ ఎలా ఉంటాయి? సే సార్ నో ఐడియా వచ్చిందా? ఏం ఐడియా వచ్చింది? అంతేనా? రైట్. ఓకే. సో కోడ్ మీకు రావాలి అంటే బేసిక్స్ ఆర్ ఇంపార్టెంట్. ఓకే. సో ఎంత బేసిక్స్ ఉంటే అంత మీకు కోడ్ వస్తుంది. సో ఇక్కడ రాసే కోడ్ అంతా మీకు అర్థం కాకపోవచ్చు, బట్ స్టిల్ యూ హ్యావ్ టు ట్రై. ఓకేనా? సో మీరు ట్రై చేయండి, డెఫినెట్గా వస్తుంది. సో మీరు అర్థం చేసుకొని రాసింది ఒక 5 లైన్స్ అయినా సరిపోతుంది. ఓకే. సో విల్ కంటిన్యూ టుమారోస్ క్లాస్.